Hello, are you able to hear me?
Yes, sir.
Okay. So the participation number of participants is kind of low, right? Was it this low in the morning for MLP?
MLP, it was around 10 to 12.
Oh, okay. Okay, I think Saturday evening is not really a very good time, I believe.
We had a DBMS session this morning. We had 6 people,
Oh, okay, okay.
and for 3 of them were instructors.
Okay. Oh, right. Oh, so this is Saturday is uh, a bad time, is it? Like bad day for having sessions, or
I think today has been like that. I don't think it's last Saturday was reasonably. A lot of people turned out. I mean, reasonable number of people turned out.
right. Yeah, I think it's surprising because usually Saturdays are like weekends, and there is a possibility of more people.
Maybe
joining.
because 2 weeks assignments have to be completed. So
Right. Okay, so let's maybe if we finish things early, we can maybe wrap up soon. So I had my plan is only to discuss this Gaussian Naive Bayes and both the theory part and the code. Right, so that is what I am planning to do, and later if we have time we can do some general discussion regarding other concepts as well.
Can I just ask one doubt before we start?
Yeah.
It's from an activity question. I just want to understand it a little.
Yeah.
Can I just read out the question? It says, given a feature vector x of dimension m in a multi-class classification problem, where each feature is a binary value, which of the following distributions are used to model pxi given y?
Okay.
And I mean, there's an answer. I mean, the options are Gaussian, multinomial, categorical, and Bernoulli. Do you want me to read out the question, or should I copy and paste?
Yeah. So you can. So far I got it. P of x given y, which they're all binary, right? Each feature is binary, and
each feature is binary. Yes.
Okay.
And it's a multi-class classification problem.
Okay. So yeah, what is the question?
So it's saying what is the distribution
right
model? Yeah. Which of the following distribution is used to model it?
Okay, Bernoulli is the one, right? If features are binary.
Yeah, that's where my confusion was. Should the class, I mean, should the label be binary or the feature be binary?
The label, right? So the feature is binary, and I think that's what the problem states, right?
Yeah, the question says the feature is binary.
Right. So if you have m features, right, and xj can take values 0, 1, then you will model p of xj given y as Bernoulli of pj, right? Something like this.
Okay. So I mean, we are basically modeling the features, right? So that's okay. That's my.
Yeah, we are modeling
because
the
always
features.
We've been looking at from the label side. Okay.
Right. So this is called the class conditional density. So that's the proper term to use. So we try to model the conditional density of the feature given the class.
Right, and because the features are binary, we take Bernoulli. Okay.
Yeah.
Silly question, but now I realize it's a silly question. Okay, got it. Thanks.
Right. Okay, so we have slightly more number of participants. Okay, so we have a quorum to start the session. See, in case we finish early, we can discuss other things as well. But the plan I had was Gaussian naive Bayes, because we did multinomial naive Bayes the other day, and this Bernoulli naive Bayes, categorical naive Bayes, they're all very similar. The formula is kind of similar, so I don't think we need to spend too much time there.
So can we at the end discuss a few practice assignment the programming?
Yeah, sure. We'll do that. Yeah.
Right.
So we are in naive Bayes, right? So the idea in this Gaussian naive Bayes is the features are all real numbers, right? So you have X is a feature vector with n features. They're all real numbers. So what we do is we try to model the class conditional density as a multivariate normal distribution, right? So a multivariate normal distribution with mean vector mu and covariance matrix sigma. Okay, so this is what X looks like. Actually, this should be XM, and to be consistent with our notation, this should be XM. And we have mu, one mean for every feature. So these are the entries of the covariance matrix. I hope this is something which should be familiar to all of you. This is just the covariance term ij, and on the diagonal you will have the variance for each feature. Right. So can you tell me what the dimensions of this covariance matrix would be?
M by M.
N by n, right? So that would be
M by
the
M.
m by m. Yeah. In this, so this, assuming we correct this, it will be m by m. Okay. So the functional form of the density, right? So this is the density PDF of that multivariate normal distribution. It will be of this form. So one way to remember this is, if you let all of them be scalars rather than vectors, then this is just minus half into x minus mu whole square by sigma square, right? So roughly that is how you understand the numerator, and denominator is kind of tricky, but it's something you have to live with, right? So this is the multivariate normal distribution. So in order to understand things, it's always easier to look at only two features, right? When you have two features, this becomes a bivariate normal distribution. And the particular case that we are going to look at is when the covariance matrix is diagonal, right? So when the covariance matrix is diagonal, what it means is that yeah, we'll come to what it means. So, but this is a special case that we'll be looking at, especially in the context of naive Bayes. This is what we'll be focusing on, right? So I hope the symbols are clear what they mean. X is a feature vector, mu is a mean vector, and this is your covariance, diagonal covariance matrix. Okay, and the whole thing is called a bivariate normal distribution. So what we are going to do is we are going to compute this density. Okay, so the tough part is this expression here, x minus mu transpose sigma inverse x minus mu. So that is what I have written here. X minus mu transpose is this thing. Sigma inverse, because it's diagonal, the inverse is just reciprocal of diagonal elements, assuming that the diagonal elements are non-zero. And then this is x minus mu, right? So if you multiply the whole thing together, you get something like this. So it's a very simple expression. X minus mu by sigma whole square.
But I didn't get that inverse of the diagonal elements. How's this coming as inverse?
Yeah, so if you have a diagonal matrix like this, right? So say A0 0B, then so if I call this B, then D inverse, right, is going to be 1 by A 0 0 1 by B, right? So this is a property of diagonal matrices. The inverse is the reciprocal of the diagonal elements. Okay, so if you, just to verify it, you can try what happens if you do D inverse. You will get the identity matrix, right? A into 1 by A is 1, 0 is 0. So
right.
okay, so this is sigma inverse. So if you multiply the whole thing, the numerator.
But in the notation is not coming as inverse. But we are assuming that this. Okay, right. Okay,
Yeah.
sir.
Yeah. Okay, so this becomes x minus mu by sigma 1, x1 minus mu 1 by sigma 1 whole square plus this one, right? So this is one part of the numerator. Basically, the minus half will get added. And if you look at the determinant of a diagonal matrix, that is just product of the diagonal elements, right? So it's just A into B. So here the determinant of sigma will be just product of the variances. So sigma 1 square into sigma 2 square. Okay, if you put all of this together, this expression on the LHS on the left becomes this, right? I hope you're all able to see how we obtain this expression. Any questions regarding this?
N being the number of features.
Yeah. N is the number of features. Yeah. Right here we have only 2 of them, so this becomes 2 pi whole square, and determinant is this.
So we have divided by standard deviation as well.
Sorry.
So we have divided by standard deviation as well. X1 minus mu1 by standard deviation.
Correct. Yeah. So is your question from where we get that, or?
Yeah, like where.
So it come.
Half as well. Like,
so it comes from here, right? See, this is the expression that we want to compute, and these are the vectors that we have, x mu, and this is the matrix. So x minus mu transpose sigma inverse x minus mu, this whole expression, right? That is this part. So I am just plugging this into this. And if you multiply by minus half and take the and e power this, you get the numerator.
so can you this question, is there half there as well in the question?
In the the minus half is there. It's a part of the. I mean, it's there, right? So it's just an extension of the normal distribution to several variables. So if you remember the normal distribution, it will be something like e power minus half into whatever, right? Minus half into
e power x minus mu.
X minus mu whole square by sigma square, right? So the same thing, instead of x minus mu whole square by sigma square, you have this matrix vector form, right? So that's all I'm doing. Very basic algebra. If you go back and work it out, you will see. Okay, I hope all of you get this part so far. Now what we do is, what do you think we can do with the numerator?
Make it a log space.
Summation.
Okay, so this is e power something plus something, right? I can write it as
multiplication e to the power.
Right. So I can just split this as 2 products, right?
Right.
So now if you notice this part on the left, this is nothing but the PDF of a normal distribution, right? In one variable, x1 mu1 sigma 1. And what you have is, here is the PDF of another variable x2 mu2 sigma 2. So we have product of 2 densities, but they're all univariate normal distributions. Is that clear?
Yes, sir.
Yes.
Right. So what
this works. Sorry, this works only in the special case where the covariance matrix is a diagonal.
Right? Exactly. Yeah. Only for the diagonal, we are like fully we are sticking to this diagonal covariance matrix case.
And just to refresh, I mean, I should know from MLF, but when does the special case happen where it is a diagonal only covariance matrix? I mean,
yeah.
Remember, but I just can't remember.
Right. So that happens when. So if you
features are independent, right?
Yeah. Okay. Right. So that is what we are leading to. So x1 and x2 are independent, right? Only then this can happen, and if this happens, then the multivariate will factor into 2 products like this. So right. So that is what we are trying to do, because see, all along I have been talking about what is this? Fx, right? This is actually f of x given p of x given y. So we are trying to model, always in naive Bayes we are trying to model the conditional distribution, right? So this is for one class. That is what you have to remember. So the features are independent, but in our context of naive Bayes, the features are independent given a class. That is what we have arrived at, right? So our area will know, our area of focus will be working with a classification problem where the features are normally distributed and they are conditionally independent given a class. Okay, is the setting clear?
Yes, sir.
Okay, so now what we'll do is we'll just go ahead and generate some data like this, which actually follows this. This is something we did last time. I'm just going to redo it now. If you want, you can code along. Okay, so the same set of things that I did last time, we'll set the figure size and all that upfront using the runtime params. So I want figure size to be, say, 8 cross 8, and what else did we set that the other day? Font size, right? So we set font size, let's say, is 15. Okay, so so now what I want to do is the plan. Okay, I'll lay it on the plan here. The plan is to generate data that is from a bivariate normal distribution with diagonal covariance, right? So this is the first thing, right? When we do this, we know that the data is, the features are conditionally independent given the label. Therefore, naive Bayes is a good option here, right? So the first step will be to generate data like this. Then we will fit a Gaussian Naive Bayes model, and then we'll see how accurate the fit is, right? So we'll see this visually, right? So I hope the plan is okay, right? This is what we'll try to do. Okay, so if you remember, do you remember what we did for generating random numbers last time? Does anyone remember the process that we followed?
I think we took np.rand.
Right. So we took np.random.default
Right.
RNG. So we took this, and for reproducibility, we set a particular seed value, right? And okay, so now what I want is, I want to generate a bivariate normal distribution, right? So I'll do RNG.multivariate normal, and my mean will be, say, let's say 1,1. Just anything will work. I'll just play around with this, and the covariance matrix will be identity, right? We want it to be identity or diagonal, but let's take the simplest diagonal matrix, which is identity. So in NumPy, do you all know how to write how to get a identity matrix?
np.i is there.
Okay, right? So np.i of 2, right? So it's just a 2 cross 2 identity matrix. Now, so the mean of this distribution from which we are going to generate will be mu, the covariance matrix will be COV, and I will generate say n samples. That also will use a variable here, say 1000 samples, right? So okay, so I have generated this. Let me call the points x. So can someone tell me the size of x? What will be the size of x dot shape? If I run this, what will I get as output?
Just get 1000 comma, right?
Okay, 1000 comma what? 1000 comma 1, 1000 comma 3, 1000 comma 5.
2.
Okay, 1000 comma 2 is it? Let's see. Correct, right? So I hope this is clear to all of you, right? So see, we are generating. See, this is bivariate, right? So the moment I say the mean is at 1 comma 1, so let me plot it. Once I plot it, it will be clear why the shape is 1000 comma 2. So how do we plot? We do plt dot scatter. It's a scatter plot. All the x coordinates will go in this array, and all the y coordinates will go in this array, right?
Colon comma 1.
Sorry, yeah. Okay, this is not looking good. So let me run this again. I think the figure size was not set properly for whatever reason. Okay, so this is good, but I'm not able to get the overall picture. So I'll increase my axis limits to minus 10 comma 10 on both the directions, right? So I'll do that. Okay, so you have a blob that is centered at 1 comma 1. There are 1000 points here. Each dot represents 1 point. There are 1000 points. And now I hope you all see why x dot shape is 1000 cross 2, right? Each one will have one x coordinate and one y coordinate, and then there will be 1000 points. Okay, is this, can we proceed now? Any doubts? Okay. So what I'm going to do is, we are going to try out a 3-class classification problem, right? Multi-class. So let's not be too ambitious. So we'll stick to just 3 classes. So one class is this, right? So let me change this to -1 comma -1, right? Let us center it at -1 comma -1. So I will call this mean 1, covariance 1. Likewise, I'll have mu2 and covariance 2, mu3 and covariance 3. Let's say this is at 0 comma 0 and this one at 1 comma 1, right? So now I'll end up generating x1, x2 and x3, right? So let this be mu1, mu2, covariance 1, covariance 2 and covariance 3, all same number of data points, right? Once I generate them, I'm going to plot each of them, right? And I also need to color them, right? Let me give them these 3 colors: blue, red and green, right? So blue, red and green. So this will be x1, x2, x3, right? So let me call this class 1. I give it a label class 1, class 2 and class 3. Okay, let's now plot it. I
Change
hope,
line number 8, 9 and 10. X1, X2.
yeah, thank you. Right, so they'll all be, I think, overlapping. So we need to fix that. They are too close. Okay, so what we'll do is we will move them out, let's say to 4 4. Okay, we are just okay, that's decent, right? So we have, yeah, so we have this setup now. And now if I want to display the labels on the plot, do you recall what we did the other day?
Legend.
Yeah, we have to do a plt.legend, right? So, and if I want to suppress this line when I run the cell, what should I do?
Semicolon.
Semicolon, right? So okay, so we have class 1, class 2, class 3, 3 blobs. We'll be trying to classify them using Gaussian Naive Bayes, right? Uh, so first part is done. We have generated data from a bivariate, from 3 bivariate normal distributions with diagonal covariance matrices. Okay, that is what we have done. And this is a 3 class problem. Okay, I hope it is, the setup is clear so far, right? Shall we proceed?
Yes, sir.
Okay.
Sir,
Yeah.
can you explain this again, sir? Code you have written.
You must tell me which part you didn't understand so that I can explain that part alone.
Sir, you have find out here mu1, mu2, mu3. So this mu1, mu2, mu3 are, sir, this is mean vector.
This is mean vector, one of these, some point in the 2D space.
Sir, here you have mentioned here multivariate normal here, but you said that you are actually working on the bivariate.
Yeah, so multivariate means anything above 1 is multivariate. So in our case, we can only visualize 3-dimensional is possible, but it is messy. We can only think about 2 dimensions, right? So we are sticking to two features, and therefore it is bivariate.
Okay, sir. And in line number 4, what is RC? RC params you have written here.
RC params is called, so it is called runtime configuration.
Okay.
That is, so these are, see, the RC params is one dictionary which has all these configurations like figure size, font size. It can, how do I put it? So certain parameters that will that will change the way your plot looks.
Okay. Okay. Thank you.
Okay, so see, one suggestion for when you learn a library is try to focus on the smallest number of commands or methods that will give you maximum control over what you want to do, right? So I mean, this will come with experience as you spend more time with the library. We must always try to see, for example, what I'm trying to say is, if I remove a single parameter from any of these methods, the code will not work, right?
Yes.
As I want it to. So for example, if I remove the label from this particular, what will happen is the class 1 will not get displayed, right? So it's a general suggestion is to whenever you call a method or an API from a particular library, try to be very clear why you are having each parameter, right? So here I know I am adding a mean, right? And without the mean, it's not going to work, right? So that might be very useful later on.
Okay, sir.
Right. Okay. So we are done with this part. Now we have to fit a Gaussian naive Bayes model, right? So that's what we'll be doing. So for that, we need to go back to some very brief theory. Right. So P of x comma y is this is basic probability. P of y into P of x given y. P of y, if you recall, is the prior. P of x given y is the likelihood. Right. So P of x given y is a multivariate Gaussian with what covariance matrix? If you all have been following so far, fill in the blanks.
Diagonal.
Okay, right, with diagonal covariance matrix. So that is when Gaussian Naive Bayes is most effective, right? Because features are conditionally independent given the label. Okay, so how do we estimate the parameters? Maximum likelihood estimate, right? So we do MLE. If you have n data points, then you take the product of the joint probability, right? X superscript I recall is the data point. So you do this. Now, how can I decompose this second part? P of xi given yi.
Using the normal
Right.
multivariate normal.
True, right? So that is correct. Is there anything simpler I can do since I know that it's the diagonal covariance matrix? And given that we are doing naive Bayes, right? This is naive Bayes.
Product of all each features.
Correct. So product of each feature. Okay. Now what is P of xj given y? What form will it take?
It will be like a single variable normal, is it?
Right. It will be a single variable normal. So, okay. Now I'm moving to the log space. Okay. I'm doing the same thing, but same expression. These products become sums. So log of P of xj given y will be just log of that normal distribution, right? So I have just substituted that here. Right. So if you recall this exponential term, right? E minus half into x minus mu whole square by sigma square, that comes out, right? The log of e power something. You have this big formula, and you have to differentiate this with respect to mu and sigma, right? Mean and variance, these are the two parameters. So you differentiate that and you end up with something like this. Okay, I think this still here you would have seen in the slides. Is everyone clear with this formula, or do you want some more clarity on what this formula means? These two that you see on the screen.
Yes, sir. Please clarify.
Okay. See, this is this is the estimate of the mean for the jth feature and the class C. Okay, J is the feature, C is the class. Okay, for example, in our case, if there are three classes, right? Mu 1 will be, there will be two mu's, right? For each blob here, there will be a mu1 and a mu2, right?
Yeah.
So there will be 6 such mu's. That is what I have written here. So mu11, mu12, mu13, and so likewise mu21, mu22, mu23. So they will be the means for the jth feature and the cth class. Okay, that is the left hand side. What it says is, do you understand what the denominator means?
Number of class C.
Right. So it
I
is.
mean, if it is 1, the total number of class 1, summation of how many number of class 1 is there.
Right. How many class C? How
Class
many
C is
points
there,
are
yes.
from class?
Class C, right.
Yeah. Right. So that is the denominator. What you are saying is that, filter out all the points that belong to a particular class. In this case, class C. That is the denominator. Okay. The numerator is telling you, out of those points that you have filtered out, add the jth feature of all these points. That is the numerator.
Right.
Okay, so that is the numerator. Once you estimate the means, then you can estimate the variances using this formula. This is, if you recall, this is just sample variance, right? X minus mu whole square, you sum it and divide by n. That's what you're doing. So this is just a simple mean. simple average x1 plus x2 plus x3 by 3 we do, right? That is what this left hand side is. Okay, is this clear? Because if it is not clear, the next slide will not be clear.
Yeah, so mean is like this is simple calculation that I understand. What about like different, if there are multiple features, then there will be multiple means or how they will be combined?
Yeah, when there are multiple features, you will have a mean for each feature, right?
Okay.
So there are 3 features and you will have 3 means. That is just for one class. So if there are 10 classes, then you'll have 30 means.
Okay. Okay.
Okay, so I hope everyone is clear with these two expressions. So because the next step is I'm going to vectorize the whole thing. Okay, did you all get what this slide is talking about?
Yeah, the form is okay. I think when we implement, we will know how it gets implemented.
Right, right. So only change is that this j has gone out, right? So I'm representing the mean for every class here on the left, right? And since I'm just adding up the feature values xj one feature at a time, I'm just vectorizing the whole thing, right? Rather than doing it feature by feature. See, for every feature we divide by n. For every feature we add xj for all the n all the points in that class. So why do it separately, right? Why do it separately? You do it at one go for all the features in a particular class. Okay, so I hope that you have got this and we can then go ahead and code this.
Yeah.
Okay. Right. So before we do the estimation, what I would like to do is I would also like to generate the labels. Right. So let's say this is going to be np.zeros of n. So what will be y2? Can someone tell me what y2 should be?
Can be 1.
What?
1, right? So what I'll do is I'll just do 1 plus y1. Right? So these are all class 0, these are all class 1. And y3 will be 2 plus y1.
Or 1 plus by 2.
Yeah, or 1 plus y2, right? Both are correct. So let me rename this as class 0, class 1, class 2. Okay, so now again, someone please fill this up for me. So I need to create a data matrix, a feature matrix X and a label matrix. Sorry, not a label. Okay, actually we need a label matrix, right? Or never mind, we can just stick to a label vector, right? So can someone tell me how do I get hold of a feature matrix given x1, x2, and x3?
Concatenate.
Okay, we'll concatenate this np dot concatenate. I'll put all these 3 in a tuple. Along what axis should I concatenate?
Zero.
Axis 0.
Right. So let's concatenate it along 0, and for y, we'll just concatenate, right? It's just a vector, so we don't need to worry too much. Okay, so let's verify it before we proceed. X dot shape and y dot shape. So we have 1000 points each, so this becomes 3000 cross 2 feature matrix, and 3000 cross 1 or 3000, right? That's the label vector. So once we have this, what did we do? If you recall, what was the next step that we did? So what should we do now?
Train and test split.
Yeah, we have to split it into train and test, right? So from sklearn dot model selection, we do a train test split. Okay, so we just split it as train. Okay, so we just split this. I think the test size can be something like 0.2, and we also need to give a random state, right? So (42), right? So we will verify if we have split it correctly. Okay, around 1800 points. Okay. Why am I getting different shapes here? Do you all see why?
Should be extrain.
In test,
X
extrain,
test.
X test,
Oh,
extrain, then X test, like train test, train test.
Yeah.
Yes. like
oh,
that.
okay. First the features and then the labels, is it?
Yes.
Okay. Okay, so what? Okay, so this is, we have done the splitting also, right? We have done this split. So now if I want to ask you one question on top of this, right? So can someone tell me how will I estimate the number of points in class 0 in white train? If I give you white train, you need to tell me how many points are there that belong to class 0. How will you do this?
Put np dot where
Okay.
is equal to 0.
Okay, equal to 0. Okay, I'll just say that this is 1 and rest are all 0. And what should I do? This will give me a vector of
Sum. NP dot sum.
np dot sum of this, right? So, okay, we have 585 points in class 1. Sorry, 585 in class 1, meaning class 0, 607 in class 2, and 608 in class 3. Roughly they are equally distributed, right? So around 600 points in each class. So that is good. Okay, so once we are clear about that, we can finally start writing our method to fit the points, right? Okay, so here we need the help of few images, right? So that things kind of become clear what we are up to. So assume that you have your feature matrix. So this thing is your feature matrix, right? So whatever you have on your left here is an array. It's a NumPy array of size 9 cross 2. Okay, so all the blue colored ones are class 1, green ones are class 2, and red ones are class 3. Okay, so the first column of this matrix will be feature 1, second column will be feature 2. And each row will correspond to one data point, right? So it's a feature vector. So this is, for example, the fourth data point, x4. x4.1 will be feature 1 and x4.2 will be feature 2 for the fourth data point. Okay, I hope this NumPy array visualization is clear. So Is there any question here?
No
Okay.
question.
Sir, no.
Yeah. So now what we want to do is, if you go back to the formula, right? We need to, first thing that we need to do is we need to extract all the points from the training data set that have a particular label, right? So I need to, for example, get hold of all the blue colored points, right? So how do I do that is the question. How do I get hold of only the blue colored points, and maybe then the green colored points, and then the red colored points? So how do I do that?
Can use NP where?
Okay, NP where?
Yeah.
Okay, so we can use NP where. That's a good one. It turns out that there is an even simpler way to do it, right? I'll just write it down. Okay. So X is the feature matrix, right? X train. So assume that I am writing a fit function where I have passed the matrix, data matrix or feature matrix as X and the label vector as Y, right? So I'm trying to write the fit function. So as I said, one of the first steps that we have to do is get hold of all or filter all data points that belong to class C, right? So if X is my feature matrix, this I'm telling you that this will give me all the feature vectors that belong to class C. Now, does everyone follow this, or is this not clear?
Clear, sir.
Okay, right. So this is, everything kind of depends on this now.
This is quite powerful in NumPy, isn't it?
Right. Yeah, this is a very powerful thing. Right. So I have now filtered all my blue points. So for example, here it will be YW equal to 1. Right. So once you have filtered it, all that I need to do for estimation is get the mean of all these points, right? I just need to sum all these points, and I need to sum them across axis 0, right? Not across axis 1, but across axis 0, because I want this sum of the rows in some sense. Okay, so what I'll do then is I'll do x underscore c dot mean of axis equal to 0. And the next part is what? The variances, right? For that, I'll simply do x underscore c dot variance x is equal to 0. So I'll do this for each class, right? In the total number of my classes. Okay, now how do I estimate the number of classes? Can someone tell me how to do that? If you have access to Y, the label vector.
You have to take
Find the unique values and
Unique
the
values,
count.
yeah.
Okay, so you just get hold of the unique values and okay, so I have now estimated the mean and the variance for each class. Okay, now I'll go back to this image. See, the mean and variance will be what? Some vector of size of length 2, right? For each class, it will be a 2-dimensional vector, mu1, comma mu2. So for 3 classes, you will have 6 values. Okay, so I'm now representing that in the form of another array, right? Another array of size 2 cross 3. So for each class, you have 2 means corresponding to the 2 features. So I'll put all of them in one 2D array like this. Okay, so that is what I'm going to do now. I'll I'll say means will be np.zeros of. Now what should be the size of this array?
Six.
Discover number of
Yeah.
Classes by features.
Okay.
Class.
So it'll have some number of classes here. Now, so let me put this here. I need the number of features. How do I get the number of features?
X dot shape and index 1.
Okay, x dot shape of 1, right? So that is the number of features. So yeah.
Just
so,
one thing, sir.
Yeah.
On line 6, instead of getting the number of classes, shouldn't we like get the list of classes? Like, we should not get the length, we should get the actual classes, because we have to loop and compare with the actual class.
Loop and compare. Sorry, I didn't get that part.
In line 10, we are saying y double equal to c, right?
Correct.
So it will work only if we have the actual class, not the index. So instead of length in line 6, we should have the actual classes.
Yeah, agreed. But here, so here we have taken the liberty to call the classes 0, 1, 2, right? So 0 to n minus 1. If there are n classes, so it is
By
like
chance it will work, but I think we should be correct.
correct. But I choose how to model the classes, right? So someone can give me the data as in how they want to give it, right? So for example, they can give me the data with class names as red, blue, and green, right? But it is what I will do at the pre-processing stages. I will map them to 0, 1, and 2. Right? I know that the code in the collab in the lecture was done differently. There they were looping over. There were some 2 loops and all that. X, idx. I hope you remember all that, but I somehow don't want to do it that way, right? So, see, 1 loop is enough in my opinion.
So, can you explain the doubt? I didn't understand. What was the doubt?
So, the classes, so Bhupesh, I think, let me know if I understood it clearly. This classes need not be 0, 1, 2, right? That's what you're saying. They can be anything. Can be 1, 2, 3.
Yeah, we should remove len basically.
Yeah. So that is the point, but I would say that len is enough, right? Finally, it's a multi-class classification. I have abstracted out all the class labels. For me, I just need to know the mapping between what the customer has given me, say red, blue, green. I choose to call red as 0, blue as 1, and green as 2, right? As long as I'm clear about that, I can stick to len of n number of classes.
Okay.
I hope that is fine for everyone. Okay, so so classes are indexed using 0, 1, 2. That is why this length of classes works for us. Okay, so
Even
this is
if we remove len, still it will work.
probably it returns 0, 1, 2, right?
Yeah.
Okay, fine, got it, right? So but since I've used, see, I want n classes to be a scalar, right? I think this will return an array. I prefer to have n features and n classes as scalars.
If we not remove, even if we remove the length, we can use enumerate to get the actual values in the n classes. So it will return the values and the index together.
Correct.
That way also it is possible.
That is also possible, but I want to keep it
simple. Yes,
simple,
yes,
yeah.
only yeah.
Okay, all your points are valid. So there will be certain places where I deviate from what is given in the collapse. So please don't mind that. Okay, so this so far so good, right? So means you all understand that this has to have shape, features, cross classes. Okay, I have to do something similar for the variance. So once I do that, what should I fill in here? This is the mean for what?
C record.
Correct. This is for class C. So what is the correct syntax that I should be using here?
Colon comma C, right?
Colon comma C. I think that is correct. Okay, so here also it is colon comma C. I hope you're all able to see that. See, let's go back to that image. Colon comma C. So you fix the column. The column here is the class. Say, for example, you are computing the means for class 2, then it is colon comma 2, right? And that colon will mean that you plug in all the values for that particular column, right? Second column in this case. Okay, so once you have the means and variances, are we missing something in terms of parameters that we have to estimate? Is this enough? If we compute the mean and variance, is it enough?
We need the prior also.
Okay, we need the priors, right? So priors will be of what shape will the priors have?
One dimension only. It's only for one y, right? Priors of y.
Correct. So what should it should be zeros of what?
Classes.
N classes, right? So it should be zeros of n classes, and priors of C is nothing but what?
So your line 10 is double S zeros. Zeros.
Oh, sorry, zeros. Okay, priors of C, class C. What is the prior for class C? How do I estimate that?
Number of C count of C by total number of variables. Count of a particular class divided by total number of n. I mean, n is the.
Okay, can you tell me what in terms of? Can you tell me what the numerator should be?
Yes, count of C.
Okay, you're saying
Features.
Exceed or shape of 0.
Yeah, xc dot shape of 0 divided by
X dot shape of 0.
correct, right? So that is correct. So that is priors of C, means variances, right? So let us move the priors here and say that this is you're estimating the priors. I think that's clear, and this is for the class conditional densities. Okay, so
just to be clear, so priors xc dot shape dot 0 I understand, because that's basically the instances where we found y is equal to C, and divided by x dot shape dot 0, but I mean it's really y dot shape of 0. Both are the same, but what we're really counting is the number of y's, right?
Yeah, number of data points that belong to a y dot shape of 0. You could call that number of points which belong to that particular class.
Right.
We could. Yeah, you are right. That might be more appropriate. So what I will do is probably you can just abstract. I mean, make this a variable number of points, right, in the data set, and say call it y dot shape of 0, and so you have total this many data points with these many features and these many classes, right? And we are comment is inappropriate here. It's more appropriate here. So what comment would I write here? And just say estimate the parameters for each class, right? And you first filter all data points, and then you rest is self-explanatory. So this is to initialize the params, and this is Okay, finally I return them. We are now in a good shape to return the priors, means, and the variances. Okay. So is this function clear? As a function, is this clear? Okay. So so fit a Gaussian naive Bayes model. We have fit the model. Now we just run this and see what we get. I'll call fit on X train. PMV, right? Priors, means, and variances. Okay. First error we have no.
It's double brackets, right?
Right. Should be a tuple. This should also be a tuple. Okay, that is our first error fixed. What other errors? Okay, we don't seem to have any other errors. So let's print them and see if we have some reasonable values. Priors, okay, I'll print them on separate lines so that we are able to distinguish the three. Priors, means, and vars. Okay, priors are correct, nearly 1/3 each. Okay, means are how do I view this? I should look at it as columns, right? So class one is -4, -4. Class 2 is 0, 0. Class 3 is 4, 4. I mean, class 2 is 4, 4. Right. So we seem to be getting it more or less correctly. And if you look at the variances, they should all be near 1, right? So because we had a diagonal covariance matrix, the variances of the variable should be 1. Okay, so now we can peacefully go ahead and do the other parts, since we know that the fit is working correctly. So let's now go to this part. Once we have fit the model, then we have to infer, right? Do I have to go ahead and predict what
So
will
one
happen?
second.
Yeah.
Like how is it like all the variants are near to 1? I didn't get that.
So that is because the data comes from a identity from a distribution. Okay. So yeah, maybe before we proceed, let us just see what happens if we change the covariance matrix to something that is non-diagonal. So if I change the covariance matrix to non-diagonal, what assumption will break down?
Independence.
Right. So the independence assumption no longer holds good. So let me add something like this. I am adding some off-diagonal elements, right? I'm making it 0.9, 0.9. So let me call this so that I can customize this also later. Call this some off-diag matrix, right? Off-diag. Okay, so you have this very nice linear correlation between these two features. They are very well correlated, not at all independent given the class. Now if you fit will run properly, there's no point, there'll be no problem there. Priors are okay, but if you look at the means, it's not too bad. So remember that the means are supposed to be -4, 0, 0, and 4, 4. Right? So even the variances do not seem to be all that bad. Okay, so now what? So I seem to be getting the means and variances correctly. Now what could go wrong? Can someone tell me what could go wrong if I use this naive Bayes, if I use this classifier to do my prediction? So did everyone get the point? So what has happened is I generated these three data sets using these means, right? -4, -4, 0, 0, 4, 4. And my naive Bayes model is able to predict those means correctly. -4, -4, 0, 0, 4, 4. Okay, so it's doing a pretty good job, even though the features are not independent. So why did we worry so much about this conditional independence then?
One might be misclassified as class 0 or vice versa because they are overlapping.
Right. Yeah. So that is one point, right? And in fact, that's the main point. So one thing we have to keep in mind is that the point of naive Bayes classifier is not to get the means correct, right? So if I use this naive Bayes classifier to predict, right, I will assume that my assumption will be that the covariance matrix is still diagonal, even though you have these two off diagonal entries of 0.9 and 0.9. Okay, so
you can't assume univariate normal distribution, right? Because you can't have a determinant that will be, I mean, that sigma inverse will all just not be possible and all.
So see, this sigma inverse will still be possible. So this form, right? This form for the PDF, this works only if sigma is invertible. So that is kind of, so there is one condition on sigma, which is that I think it should be positive definite, something like this, right? So first of all, sigma is symmetric, right? Usually this covariance matrix is symmetric. So in addition, for this kind of multivariate normal distribution, I think we need to have sigma to be positive definite. So assume that the sigma inverse will always exist.
And if does exist, still, unless it is diagonal, you can't split it into single variable.
Yeah, this is a very important point that I want all of us to understand. It's, see, there is the modeling assumption on one hand, and there is what the real world data actually looks like. Okay, so let me go back to this image. See, real world data looks like this. Okay, I can't change that. But I don't know. See, typically in real world data sets, I can't even visualize this, right? So I don't know how it looks, but I am going to assume that features are conditionally independent given the labels. It's a bad assumption in this case, but I'll stick with that because I have the liberty to assume that, right? I am the one who's modeling. So in that case, my diagonal matrix, whatever covariance matrix that I learned, right, that will still be diagonal. Is this point clear? Okay, see, there are, okay, so you need to I'll draw two diagrams here. So one is this, right? This is, let us just label this as, this is your true distribution. This is how your data really looks like. Okay, it looks something like this. Now I am learning a naive Bayes classifier for this data. Okay, and the naive Bayes classifier that I learn is, just copy this. Okay, so I will not generate anything. Instead, what I'll do is okay, I'll just use instead of mu1, what I'll use is I'll use the means that I have learned, right? So what is the mean that I have learned? M, right? M is the mean that I have learned. So M of can stop me if you don't understand what I'm doing here, but I'm going to do something slightly complicated. See, the first column is the means, right? So I'll just show the image and do this. So M of colon comma 1 or M of colon comma 0 will be the means of my first class. So that is what I'm going to do. M of colon comma 0. This is M of colon comma 1 and this is M of colon comma 2, right? And remember that for my model, right? So this is model distribution that I'm trying to generate, right? So for my model, there are no off diagonal entries. It's a diagonal matrix. So I'll set this as 0. Okay, now if you, okay, and I have to change the variances, right? So the covariance is, what covariance did I obtain? This one, right? Yeah, so this is slightly messy, but I'll have to do this. So V of 0, 0. Okay, so see, let's just let's settle for a compromise. Let's just say that these values are very close to 1, okay? And it's okay to keep them as identity, right? I hope you don't mind. It's 0.99, 0.97. It's not too much of the thing, okay? Okay, so this is not the true distribution. This is how the distribution would look if I generate points from my generative model. Okay, so do you now get the difference? This is how data actually looks like. This is the data set that is given to me, right? But I chose to model this data set using naive Bayes. And moment I choose naive Bayes, my features are conditionally independent given the class. So I will end up modeling my classes this way, right? I can't help it. That is a modeling assumption. Is this part clear?
Yes, sir.
Okay. So,
but sir, in general, how and when would you decide to use naive Bayes?
see, typically we choose naive Bayes in when we want to have a baseline. So, see, if you want to have a baseline classifier, do you know what a baseline is?
I think my assumption is that it's the rough first model that you do.
Right. So naive Bayes is that rough first model for most of the problems. I mean, I won't say most of the problems. In the domain of, let's say, text classification, naive Bayes is very popular. So you can quickly run your naive Bayes model on a problem and get a baseline accuracy, right? So you know where to peg your hopes, right? So you can say if the naive Bayes is giving you 67% accuracy, then you can, you know where to look for, right? So if some other classifier gives you say 53%, then you know that you are doing very badly. So it's a good fit for natural language processing applications as a baseline.
Why the affinity to language, sir? Because I don't see why it's naturally related to language, or why you feel like using it there.
That is something I am also not sure. So I just know that it is very popular in this area of text classification. At least see this for many of these algorithms, the popularity also stems from how well it performs on these data sets.
So maybe those features are naturally independent in text classification.
Probably.
So
right, that could be one reason.
But that is particularly something that we were told that's not the case, right? So in text, if I decide to make each of the words a feature, then for sure they're not independent, because language has a sequence.
Right,
So
right.
it makes no sense to me.
True. Yeah, I agree. See, yeah, even though it's a naive model, it still seems to work, right, for those classes of problems, and that's some reason it's been popular. I also don't know why more than this. Maybe I can do some research and get back. All right.
Generally, the business problem is taken like document classification. So document classification, you would have probably independent features of it. It's not words. It's there, like you had explained, we are taking a bag of words and then doing a classification based on that.
Mm-hmm.
So I think probably like spam and spam detection is probably the
Even in
features are
spam detection, your embeddings would still be words, right?
yeah,
Because
but those
you're
you're
working with
taking that heading as the subject as this thing. Every one subject may or may not be. I mean, you can't say there is a strong independence between each subject.
It would be, because no matter what you do with language, your embeddings will still be from words, and they are not by nature independent.
Yeah, maybe you are right.
Yeah, so I would suggest you offload this question from MLT and import it into MLP. Right? The MLP folks might be in a better state to answer this.
Sure, yes, sir.
Yeah, the reason being I have actually not used Naive Bayes at all. See, my personal experience working with machine learning models is heavily restricted to neural networks, right? Because I entered the field when neural networks were all the rage, and even now they are. So that is one disadvantage when you enter the data science field now. It's like everywhere you will see neural networks, right? So yeah.
Interesting. So you should maybe do another session on neural nets, because even that has a lot of problems regarding explainability, right?
Yeah, true. Yeah. So interpretability, explainability is a problem that we'll probably.
But that is also in use because it performs well, is it?
Yeah. So finally, it works now. So neural networks have a brilliant track record. They get your job done. So even though they are not very interpretable, they still get the job done. So that is why they are still popular. But research is going on to see how to make machine learning models more explainable. So there's an entire field that has come up called explainable AI, right? So yeah, we should discuss that someday. Where were we? We were in this, like, getting back to Naive Bayes. I hope this fit part is now clear to all of you. Right. So now what we need to do is, if you are given a test data point, how do you classify it? Right. So for that, we need to compute the posterior. Basically, it's the predict function, but I need to run the prediction. Okay. So how do I predict? Can someone tell me how I should predict?
From the log.
From the priors.
Okay, we need the priors for prediction for sure. We need the priors.
Mean and variance.
Okay, so we also need the means and the variances. Okay, so let us, since we have been using classes in the code, in the collapse, let's draw up a class. Okay, so this I will make sure that these are class variables, sorry, object variables, self.priors, self.means, and self.variances. Likewise, I do it here. Okay, so I when I why I am doing this is when I call predict, I can just call it on X. I don't need to call it on anything else, right? So yeah, so you need to compute the posterior, right? You need to compute the posterior. If there are, let's say, 5 data points in your test set, right? It's a five data points in your test set. Then your posterior probabilities will be a 5x3 array, right? 5 data points. For each data point, you'll have 3 probabilities. P of x given y equal to 1, P of x given y equal to 2, and P of x given y equal to 3. So unlike the previous cases where we were looking at axis 0, right, for computing the for computing the mean and variance, in this case, we'll be looking at axis 1 to get hold of the argmax. I hope that is clear. So okay, so let me call this posterior for POST for posterior. Now, what should be the shape of this array?
Shape of y, isn't it?
Shape of the posterior probabilities. Given X, what should be the shape?
Same as mean or variance.
Okay. See, let's go back to this. There are 5 training examples, right? So X is the test data set, right? So it's 5x2. X is 5x2. Then the posteriors is 5x3, because for each data point you need to have 3 probabilities, right? And from that you will choose which is the maximum probability. So now can you tell me what should be the shape of this?
Classes by features.
Features by classes.
So you're saying n features cross n classes, is it?
Yeah.
Okay, think again. I'll show you the image.
The opposite classes. Okay. The posterior.
See, there are 5 data points. I need to predict the label for 5 points. So there are 5 points. And if I want to predict the label, I need to know the probability
5
of...
points in the sense it's the number of samples.
Number of samples is 5.
N cross then class.
Yeah, so number of samples by...
Okay, so this should
be...
be...
classes.
Yeah, so I'll just, to make my life easier, I'll be using number of classes also. So I'll add that as a class variable. So number of samples will be x dot shape of 0 again. So
do we have to use classes out here?
No, it's not necessary. I just want it to look like a scalar fit and predict.
It was going, I was understanding better without the... I don't know about others, but it seemed better without that.
Right. See, all that I have done is I have moved the fit inside a class. That's all. Fit has no...
Yeah, no, I understand. Right.
So just why I'm doing this is, see, otherwise I'll have to pass the means, priors, variances, everything into the predict.
Right.
So the posterior is now, what will the posterior be? Let's go back to the formula. Okay, we really have to compute this whole thing. Are you interested in computing this, or do you want to see how this is computed, or do you want to skip this? there is sufficient interest, we can go ahead and do this, but otherwise we can move on.
Sir, we can compute it.
Okay, so let us first write down what we need for a single. Okay, so I don't know how to write this in LaTeX. This is, yeah, so this is, okay, now this is what? 1 by 2 pi sigma square exp of half x minus mu. There should be in a fraction again, right? So this should be x minus mu by sigma okay. Now this is what the PDF of x is, right? Correct me if I made any mistake, but otherwise I'll just go ahead. So what I need to compute is, I need to compute this for each feature and each mean, each feature in each class, right? I need to do this for each feature in each class. So rather than doing it in the original space, I would like to go to the log space, right? So this will be okay, so can someone tell me what the log will be if I take log on both sides?
The log of 1 by square root. So there will be half into minus half into.
Okay, there will be minus half into
Log of 2 pi sigma square.
Okay, log of 2 pi sigma square. So I will
Plus.
Yeah. Okay, plus
Just that, or it will be just directly minus half x minus mu square.
Okay, I will also do that part here. Okay, so it is the sum of these two terms that I need to compute, right? Okay, this may seem a bit silly, but okay, so these two terms I need to compute. So let's now go back and forth between this and this. Okay, so I'll first take this constantish term, right? So that is minus 0.5 into np dot log of 2 into np dot pi into sigma square, right? So sigma square is my variance, correct? So sigma square is my variance.
I just one doubt. This,
Yeah.
When we do np.log, it is always taking the natural log.
Yeah, I think
so. If I want to take base 2, then
so you have np.log2, I think. So if
okay.
you do np.log2, it will give you
okay.
Okay, so see, what I'm doing is I'm just very naively converting this formula into numpy. I'm not changing anything. So minus half log 2 pi sigma square, right? But remember that this sigma square here is a matrix, right? It's not a scalar, but we'll see that it doesn't matter really. So the other thing is, I just call this term 1 and term 2, right? Just to avoid confusion. This is another 0.5 minus 0.5 x minus mu by sigma whole square. So this is x minus mu by, okay, so see, x minus mu whole square by sigma square. I'll just do this I'll just rewrite this as x minus, you'll see why I'm doing this. X minus mu whole square by sigma square. Okay, I'm doing this slight change so that my numerator can be something like this: x minus mu whole square divided by sigma square. Sigma square is variance, right? So now what I'm claiming is, if I add term 1 and term 2,
0.5 and there is also 2 divided by. Oh, sorry. Okay. That's a power.
it's fine, right?
Yeah.
Okay, so the claim is, now let's look at the shapes of these things. So term 1 is, so what shape does variance have? Let's go to these images. The means and variances are of shape feature vector cross classes, right? So I list number of features cross number of classes. That is the shape of term 1. Term 2 is what? Term 2 is number of samples or number of points Okay, this is where the full effect of NumPy comes in. Cross number of. Does this make sense? Once again, I'll just keep going back and forth between these two images until I understand what's happening.
Sir, if the code is in vector form or otherwise it has to loop through.
Yeah.
Right.
So this is the matrix form. See, the code in the collab in the lectures are not in matrix form. So I want to write this in matrix form because in the matrix form it's very simple. But you have a good point. This has to be done for each class. Is that what you're trying to say?
It has to be in loop, yeah, for each.
Good point. Yeah. This is what we are missing. So, yeah, I think now this will be slightly clearer. Okay, so for each class, the variance for a class is what? Is this correct? Is this the variance for a class?
Yes.
Yes.
Okay. Yeah, good point. Thank you. I was missing this. So this is now what? Term 1 will now become just the number of features. Term 2 will become n points cross n features. Okay, which is fine. I think this broadcasting works here. I believe it works. So now term 1 plus term 2 will be for okay, so now you have computed this for each class, right? So you have to put all of these things in Okay. So now do you agree that you have to sum this along? Do you agree that I have to do this?
Yes, sir.
Okay. So is this clear to others also? Like this is kind of tough because.
Not y-axis one. Not clear, sir.
Okay. See, I will remove the sum. Okay, this is what I am doing. See, this part is clear, right? I'm subtracting the mean from each row of the matrix.
Yes, sir.
Right. So I'm doing this. Let's only think about one class. I'm doing this mean subtraction from each row of the matrix and dividing it by the variances for each row. Now I am essentially trying to use this formula. Where is that formula? I am essentially trying to do this.
Okay.
P of x given y, right? I need to sum it across the features.
Features, right.
Okay, which is what axis 1 is all about, right? Axis 1 is all about the features. So I have computed this log of P of x given y. That is what term 1 plus term 2 is, right? So let me write log. So this is the likelihood, right? But this is for all this is likelihood for each feature. So if I need to get the likelihood for a single point, then I need to sum it across the features. So that is why I do np dot sum of term 1 plus term 2. So this will have shape endpoints. Ideally, this should be just endpoints. Now this is the likelihood for class C. Right? If I add the priors for this class plus this likelihood, I will get the posterior for class C for all the points, which I can then return. Now I can now do argmax over the posterior along the first axis, and that will be my predictions. Okay, I have done several things here. Now, is any of this confusing or?
So likelihood, we need axis equal to 1 or not?
Oh, yeah, good point. We need axis equal to 1. So you are summing across all features. So the posterior will now be n classes, n points cross n classes. Okay, is this clear or is it still like kind of not so good?
I'm kind of still stuck with term 1 and term 2, the shapes of it.
Shapes, right? Okay, so see this. Yeah, so let's go to that image. So term 1 is what? Term 1 is.
Yeah, term 1 is okay. I think 2 and NPy will just get broadcast with variance matrix, and the variance matrix is basically per feature per class, right?
Yeah, so that variance matrix is one column of the variance. So this is the variance. Okay, mean and variance matrix have the same size, right?
Correct. Okay, this is one because we're looking at C alone.
Yeah, so we are looking at one column. So that is what this variance, this thing is. So this will have dimensions n features.
Right.
Okay, so that is, I think this is clear. Maybe this part. See, this part, what we are doing is we are taking x here. We are taking x and then we are subtracting one column of the matrix, one column of the
From
matrix.
Every single column of the X matrix.
Yeah, every single row, right? Because The
correct.
right, because feature, then so feature. So every column we are kind of like, we are not transposing, because here transpose is not necessary. That is NumPy takes care of that. So we are subtracting that vector from each row of x. Okay, and we are squaring it. So x minus mu whole square by, here again broadcasting works. So you are
Even
dividing.
means is broadcasting really, right? Even
here means is true. Both, so two levels of broadcasting is happening. This means is being subtracted from each row. The same vector is being subtracted from each row.
Right.
Is that right? Same vector is. This same vector is being subtracted from each row, and here the same vector is being divided for each row also. Feature 1 variance, feature 2 variance, you divide for row 1. Same feature 1 variance, feature 2 variance, you divide for row 2. So that is how you end up with the same dimension as X, the data matrix, n points cross n features. Now we are in log space, right? So we can just sum the log probabilities for feature 1 and feature 2. That is why we do axis equal, we sum it across axis 1. Is this any better now?
Yes, sir.
Okay.
I'm just trying to still just think that X is of the shape features comma points comma features, and the self dot mean is of the shape just features.
Is of the shape just features, yeah.
So how will it broadcast? But anyway, I think if you run
Yes.
it, probably know.
So this is see the broadcasting rule. I'll tell you why it broadcasts. So for example, if X is like this, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 7, 9, 3, right? This is X. And now the mean also will have two values, right? Mean will have values, let's say 3 and 4. So the broadcasting rule is that one of the rules is that the last index of both the arrays should match.
Right.
So this is some 5 cross 2, and this is 2. I mean, it's not 2 cross 1 or 1 cross 2. This is just 2. Right. So 5 cross 2 minus 2, it will work. So this will work.
Okay.
So this will be 1, 2 minus 3, 4, 3, 4 minus 3, 4, and all that. Right. So that is what will happen. But anyway, we have to still verify. So let's see if it works properly. So once we have defined the class, we can now Gaussian Naive Bayes of GNB, and GNB dot fit on X train comma Y train, GNB dot predict on X test. Okay, so these are the predictions. Now let me also write one accuracy computation. So this is true, this is predicted. I just look where true is the same as predicted, right? And I sum this and divide it by the number of data points. I multiply this by 100. I call this the accuracy, and then I return accuracy. Okay, so accuracy of X test comma predict. This is what I finally want. So let us see where the errors are. Cannot interpret 3 as a data type.
Double.
Oh, the same mistake. Okay, that is bad. Wow, we are getting 0 accuracy. That is interesting. Why are we getting 0?
What is true here?
True is the number of, sorry, the vector of labels, right? Vector of true labels.
We said
Oh,
Y
X
or
test.
X?
Oh, sorry. This is correct. This is Y test.
I think lowercase y.
All y.
Okay. Okay, we are getting 96.67. That's because we are using this kind of a covariance matrix. Let's make sure it works for the. Okay, so that I think it works. Otherwise, it won't give us this kind of a result. Okay, so yeah, that is our code for Gaussian Naive Bayes that we have. Okay, so this is one final experiment which I wanted to do and which we'll quickly do now is to visualize the accuracy of our fit. Right, for this what I want to do is plot two things. So I want to plot mu1 right. What does this come out to be? This is mu1, mu2 and mu3, right? Mu2. So what were the colors? Blue, red, green, right? Blue. And I also want to plot the predictions, right? These are the true means. And we also have GNB, that is our trained classifier dot means. Okay, so this is 0, 0, right? So this should be 0, 0 and GNB dot means of 1, 0, if I am not wrong. Let us make this black. So this will be what? GNB dot means of 0, 1 and 1, 1. This will be 0, 2 and 1, 2. Okay, so I hope you can see how close the predicted means are to the true means. Right, I mean they're overlapping. So one interesting experiment that we can do is we can make this sparse, the number of data points. We can make it very small, only 5 data points per class, and see the effect that it has on the prediction. I hope you are able to see what effect it has. Right, so we can clearly see that they're not as close as they were before. The means are slightly off.
The accuracy, what's it coming to?
So accuracy is still 100 because it's reasonably good estimate, right? It's pretty close even now. So as I said, this is a very toyish example, right? There's no challenge for the algorithm. So,
but how come the accuracy is increased, sir? It was 99.5.
That is because we have only 5 points, right? So our data set size is also come down. So we are
Gaussian
probably,
boundary is clearer.
yeah, we are probably testing it on say 10 or 20 points, for not even 10 or 20. So if you look at the shape of white test, right?
No, I understand, but intuitively it's not clear. When the data points reduces, why should the accuracy increase?
No, see, this is a generative model, right? So what we are trying to see, we have been very liberally assuming a lot of things that, yeah, your point is very valid, but here I assume my assumed distribution and the true distribution are the same, right? So even though I got only 5 points each for each class for training, that was enough for me to get a reasonably good estimate of the mean of my assumed distribution, right? So uh, in some sense I have managed to completely model the actual distribution, right?
Mm-hmm.
So my accuracy is naturally going to be high. So here the reason for accuracy being high is just that we have managed to capture the true distribution by assuming it so perfectly that the accuracy turns out to be 100. See, here there are only 5 test points, right? So naturally it will be 100. So you have to give the model several more test points which are on the boundaries of these two classes, right? At the point of intersection.
So can you just increase it? Let's see it to 10,000 points.
Yeah. So yeah, I can do that, but I need to, let's say, I'll make the test size say 0.99. Okay, now if I make the test size 0.99, I also need to change this n to this. See, I guess there will be only 1 point for training, and that's too little. So let me go back up and okay, so nothing is coming in one class. So I guess this size is too small, too big. So we call it 0.90. And just to give us all a better idea, it's better to plot only the training data and not the whole data set. Just give me a second. This will take some time, but it's worth it. I hope you see what I'm doing. I am only plotting the training data and not the whole data set. So okay, so there are 36 points for training, and how many do we have for testing? We have y test dot shape of 0. Okay, we have 324 points for test. Okay, so the accuracy is somewhere around 99%. Right? Is this more convincing now?
Yes, sir. Yes.
Okay, so it was because of number of points. Maybe we can even, where is this test? We can make it 0.95. I don't know if it will work, but yeah, now only 18 points are there. So accuracy has now come down, 97.37. Okay, so that's all I had for Gaussian naive Bayes. So we are any questions that any of you had in general?
Sir, if we have that precision recall and all accuracy, all these values are like, if when I implement with the given from the the source same kind of thing, implementing, it's giving 0.45 or something like that. So what we can do for bettering it?
What it was so
Like
sorry, I
if
didn't
we
get
find that it is accuracy and it is low, while after predicting it and we are checking the metrics, it is if we see that it is 0.3 or 0.4, what measures we need to take it, how to improve it, or what
you
to
are
do
talking
next?
about it from the point of view of the PPS, GRPS.
No.
No,
And
right?
in general, if we implement algorithm.
Oh, if in general, some machine learning algorithm you have implemented and the
Yeah.
accuracy is low.
Yeah.
What to do?
So
you're asking.
what to do next?
Okay, so there are some things that you can do. See, if it is a gradient based algorithm, if you're learning the weights of the model through gradient descent, then you can spend some time debugging that part, right? So your hyperparameters may be off. For example, the other day we were using a very high learning rate and it was not working. So
yeah, that is still we have something to change and work out. But here in this week we have Gaussian and all this naive Bayes. We don't have much values to play with, right?
Correct. Yeah, here you can't do much. See, that's why I said.
One question: can we not? Maybe the priors are. My assumption about the distribution is wrong in the priors. So could that be if I change if I try some other distribution?
Yeah.
Maybe I get a better prediction.
True, that might work, right? So you could play around with the distribution. So the choice of distribution is again a hyperparameter here, right? So you could try some other distribution for naive Bayes. But in general, options are limited, I would say. For if you want to see the possibilities with naive Bayes, it's limited.
Okay.
Okay, any other questions from anyone?
Maybe something that I totally missed out. We are not calculating any loss for this, is it?
Yeah, we are not calculating. So it's a good point. So we are see here we are directly estimating the parameters, right? We get a closed form expression for all parameters, right? So we don't necessarily compute a loss and see how the model is. So in iterative algorithms, right, in gradient based methods, the loss played a very important role in guiding the learning. So you knew if the model was learning or not based on computing the loss at every stage in the process, right? But here you don't need that because you are directly able to estimate the parameters.
Okay, now I understand the real purpose of loss. Earlier I used to think of loss and evaluation. Of course, for classification we had separate set of evaluation parameters.
Right. Okay, so the loss guides your, in fact, in practical, when you actually start building models, right? So you will be watching the loss very carefully. If the aha moment comes when your loss first starts going down. Because
so is this feature peculiar to the generative models that we don't we just see?
I think so.
Okay.
Right? Because most of the for some discriminative models like decision trees are there, which are not typically trained in a gradient based way, right? So from the list of algorithms that we are going to learn, right? See, linear regression, this perceptron.
Even KNN would be like naive Bayes.
It would, yeah, KNN. The only different algorithms are naive Bayes, KNNs, and decision trees, right? Of course, ensemble techniques are there, but some of them here are non-gradient based. But neural networks, support vector machine, softmax regression, logistic regression, perceptron, least square, linear. Everyone, all of these folks use gradient descent.
Right.
And anyway, if you start working on neural networks, right? I mean, nowadays everything is about neural networks. So the only way is to see what's happening to the loss. And okay, so any other questions? If not, we can maybe call
Sir,
it.
one more. That in that implementation, sir has given the probability, like calculated the probability, right?
Right.
Like that equation, if you can just explain, it is like giving exponential of that predicted probability, predicted something divided by expand dimension. So I'm not getting what it is.
See, that is what actually we did here. We calculated the probability in predict, right? So the whole thing here is a probability computation. The expand dimension can be tough. Where is that? Can you give me a link to the timestamp? And if you can give me a link to the timestamp, I can directly go there.
1 second.
So in this probability, is it that we have to not only take the price and likelihood of the numerator, but also the total probability in the denominator?
That denominator we can skip, right? Because that's constant. So we only need the, okay, this
so
is
if I need to calculate probability, I'll have to take the denominator.
Yeah. That is true. So even then what I would do is I will just, you can do, to get the probability, you can do posterior divided by posterior dot sum across what? Across
This is
all
still in log
classes.
space, no? So we'll have to convert it back to it.
Correct. This is still in the log space. You are right. So how do we do that? This is not really the posterior. This is, so if I do this, will it work?
Yeah, the numerator works, but the denominator is where he has used some expand dimensions and all that, which is a little confusing.
Okay, can someone show the?
It's lecture 6.4, around 11 minutes.
Lecture 6.4. Do we have this MLT? Okay, so
11th minute, I think.
11th minute, okay.
Yeah, I mean, I can around 11.
Okay, what is this? We are calculating likelihood, product of likelihood and prior. Okay,
that is just a simple prediction. The next one, predict probability.
Predict probability. Okay, calculate probability, likelihood prior. Okay, and then
numerator is just takes the exponential. The denominator is what is confusing.
Okay, so this is
this is total probability. What you do in Bayes theorem.
Yeah, but what is expand dims?
So that he has done for making sure that the broadcasting works. So for example, let's do that part here. Let's also compute probability, like using whatever code we have. So I will also divide this into predict. So this will only give me the posteriors, right? So this will give me the log posterior in some sense. Probability, right? So that's what we want. So if I run this predict underscore, I get this, right? So this is what? Let me go back to the lecture. I will keep these two side by side. So This is of size what? Post is of size number of points cross number of classes. Okay, now if I were to compute the probability, I will do np dot exponential of posterior, okay, and divided by np dot exponential of posterior. If I want to sum this along the first axis, that will give me what? The denominator will have number of points, right? Yeah, so can someone tell me what the shapes will be of these two? Number of points cross number of classes. This will be number of points. Okay, so this is a dimension mismatch. Do you see that? These two will not, we can't broadcast these two.
Yeah.
Okay, I'll just show you. We'll just let's just run this and we'll see what happens. So I want to do gnb dot proba of x. Okay, I have to run this first. So it will show me in line number 45. Okay, didn't I just? Okay, so you see the value error here, right? Operands could not be broadcast with these two shapes. So this is number of points comma classes. This is number of points. So you can't divide a 360 by 3 array with a 360 by array, right? So the last dimension should match. Here they don't match. It is 3 in this case and nothing here, or 360. So there is a there is this way of doing it is correct. You expand dimensions, but you don't need to do this that way. You can do it the following way, basically. So you just need this 360 by 3 to be divided by a 360 by 1 matrix, right? So you can just do reshape of -1, 1, which is what that expand dimension is doing. Okay, do you get what I have done here? So
So the denominator is the sum of the posteriors.
Denominator is sum of the posteriors for all classes. See.
For all classes. Okay.
Yeah, see, this expand dimension is actually nothing. It's very simple. So you don't need to do that. So using expand dimension, in fact, this Anand there was mentioning you can do reshape, and that works. That's what I have done here. That's much easier. So this expand dimension, we'll just clarify that part. So I have a matrix like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so what I want to do is I want to divide. See what we are doing here. What we intend to do here is what you have some sum for each row, right? And you want to divide each row by some number. Correct? That's how you get a probability, right? So you're summing across the axis 1 and you want to divide that number everywhere, right? So you want x dot sum of axis equal to 1. What would that be? Let's first compute that.
Bracket is missing.
Before 9, there is a opening bracket is missing.
Oh, sorry. What is the sum? 1 plus 2, 3, 3 plus 4, 7. That is what this is, right? And if I want to convert this into probabilities for each row, I need to divide 1 by 3, 2 by 3, 3 by 7, 4 by 7. That's what I want, right? So how do I do that? The way I do that is I want to make this 5 cross 1. See, currently, let me call this y. Currently, the shape of y is 5 comma. Right? If you run this, I want to make this 5 cross 1. So one way to do that is to expand the dimensions of y along the first axis. Right? So I'll call this z. So if you now run z dot shape, z will be 5 cross 1. That is all he's doing here.
Clear, sir.
Okay, got it, sir. Thank you.
Okay, so what I would suggest is you don't have to do expand dimension. You can just, if you want to divide x by its probability, just sum it across the first axis and reshape it to -1 comma 1. Now if you print x, or rather if you print this, that will be all probabilities.
Okay, sir, got it. Thank you.
Yeah. Okay, then I think.
Sir,
yeah.
one last question, sir.
Yeah.
Before. So what, I mean, you must be referring to some books or the thing. What could you recommend? What do you refer to?
So I see there are a mixed set of resources. I don't refer to a particular book per se.
Okay.
There are, for certain sections, this Bishop's PRML is good, pattern recognition and machine learning. So
for Naive Bayes, what do you recommend?
Naive Bayes, to be very honest, I don't know from where to look for, right? Naive Bayes was more or less like a crash course in probability, right? So
right.
I don't know. Sorry, for the Naive Bayes, I don't know a proper book to refer to, but in general, right? If you want to look up some resources, there is this course called Learning from Data. I think in Caltech. So if you look at there is a playlist. Okay, there are 18 videos in this playlist by Caltech.
Right. Sir.
There are some extremely good videos here. I mean, I don't know if anyone has done. You can go through the comments, right? So see, there's someone saying, even though I've gone through numerous tutorials and all this is invaluable, right? So this fellow, Professor Yasser, that is his name. So some lectures are wonderful. The first lecture is like, it gives you an overview of machine learning, what it does, right? What is learning and all that. And for week 8, I would suggest that you go through lectures 14 and 15, 14 to 16 basically.
Right. Sir.
So for week 8, that's wonderful. For the first few weeks, this is good. The linear model, I think he does regression basically. So this is, I think, basic linear regression, how it works, right? So he has used notation. His notation will be very close to what we are using in the course, W transpose X, all that. So
right.
Book per se, I'm not very sure, right? So
no, this is good enough. Thank you, sir.
Yeah, sure. Okay, then I think that's all we have for today. We'll meet later.
Yes, thank you.
Okay, thanks a lot, everyone.
Thank you so much.